All right, guys. Hey, all right. I'm just trying to get my stuff open here. Welcome. It's Q&A Friday. It's a Tech Friday for as Willie puts it. See who we've got out here. We got Robert from Omaha. And hold on. Yes. Robert says, "Am I on? It's -4 where he's at." I was just talking to some people from Chicago. They said it's -10. We've got Education Power, Robert from Omaha. We've got Steve on the line. Yeehaw! And morning, David. It's cold. You got 4 below in Omaha. Laurel, we got research in the house. Chilly Midwest, and I think so. Pittsburgh and the East Coast is supposed to get dumped on, Laurel, and we're going to get a bunch of snow, and hopefully I can fly out of here. If not, I'm sure it'll be a mess trying to travel next week. David Englehart, sunny. You know what? You had to rub it in, David, didn't you? Sunny Florida. Give me a break. Come on. Oh, man. Smash that like button. Don't forget. That's right. Thumbs up. All right. Good morning. Excellent, Steve. Everybody, excellent. David Englehart in the house. And then we got Columbia. And you know what? Oh, Felix, I didn't see if I had a UL listing on that, but my Columbia roast, I'm into the espressos, the cappuccinos, the mochados, the cucarachos, all that good stuff. I'm having a blast with my machine. So thanks for joining in. And Thomas, good afternoon from Baltimore Washington Airport. Excellent. All right, so Q&A Friday. Where we left off last time, folks, we went through some industry hot topics. Everybody knows April 9th is the big day. Finally, this computer finally decided to shut down. Let me just unplug this and get it off of my table. So we went over that. We had a good discussion about 110.14, and I want to just explore Article 310. I want to enlighten you on something that I learned. And when I shared it with a few inspectors, they were like, get out. I think you're going to like that one. And that's in 310, actually. That's why I was opening my book. I think it's a 310.12 discussion. Let me look. 310. Yes, we're going to talk about 310.12, and I'll tell you what, it's these events when I start reading the code and with the questions that come in, and you got Steve harping in on incident energy. Absolutely, it cannot be forgotten. So my phone is going berserk. I don't know what the heck's going on. I got a hard stop at 1 o'clock, but I do want to make sure that I saw the dog frozen to the tree. So I do want to make sure we cover some selective coordination topics, and the selective coordination topic I want to hit. I've got a medium voltage. There's an important topic. I think it's 240.11 discussion. I think, let me just double check, 240.11. So you can take a look at 240.11. It's going to be a 240.11 discussion. And that one came in from one of my, one of our services division individuals who was like sort of dumbfounded a little bit at what was missing in the code. So we'll talk about 240.11. We'll talk about the ground fault currents, and selective coordination. I think that's another one, Steve, that's always forgotten. It seems like we put our mind in the three-phase bolted fault world. We completely forget about the ground fault world, but we can't lose sight of that. So I will talk about that. We'll talk again. I keep getting questions about coordination versus selective coordination. I just saw a specification was sent to me, and they said the engineering firm said it shall selectively coordinate to 0.1 seconds. So I want to cover why that is an absolute insane thing to say and write down in a specification, and I'm going to draw it out and help you understand that. So we got ground fault, we got coordination versus selective coordination, 240.11. Oh, and I do want to hit 310.12, I think it is. 310.12. Yeah, 310.12. And all right, so first steps first. Selective coordination. So selective coordination is a defined term in the National Electrical Code. Hopefully everybody out there has their copy of NFPA link. I tell you what, I should get a percentage of the sales of NFPA link. And I think you've got to go to coordinated, selective. Just double checking. Yes, coordination. I'm going to see if I can get this right. Cam A monitor right. I did it. So coordination selective, this is the definition. Take a look at what it says. And remember what the concept is. The concept is the fault closest to the circuit breaker closest to the fault is the one that clears. So it says localization of an overcurrent condition. Remember, overcurrents can be short circuits, ground faults, overloads, all of that. Overcurrent condition to restrict outages to the circuit or equipment affected. Let's just stop right there, because right there, that's telling you when I say an overcurrent condition, overcurrent is another defined term. Overcurrents include overloads, short circuits, ground faults. My fault, your fault, nobody's fault. It's a overcurrent condition, and I'm exceeding the rating of the equipment. All right, so I just want to make sure that's clear. Accomplished by the selection and installation of overcurrent protective devices and their ratings or settings. Let's stop right there. So we need to select overcurrent protective devices, whether they be breakers or circuit breakers or fuses or relays. These are overcurrent protective devices. Overcurrents, again, defined term. Ratings, meaning the what do you call it? The long time pickup and things like that, interrupting ratings, all of that jazz. For the full range of available overcurrents. We didn't say for the full range of fault currents, we said for the full range of overcurrents. So that's another important piece of this definition. And we go from overload to the available fault current. Now, available fault current is another defined term. It's the maximum amount of fault current at any point in a power distribution system. And it says, and for the full range of overcurrent protected device opening times associated with those overcurrents. And that's the critical function. And if there would be anything that I would say is the primary difference between coordinated systems as they're applied in, say, 517 and selective coordination, it is that we're talking about the relationship of current with the clearing times. All right. So, master homeowner, I see notes here. Hold on. For some reason. All right. So, forgot that. I've got to always harp on that. NEC medium voltage. I'm not paying attention yet. I'm still finishing up element ICF training. All right, that's okay. You can always hit rewind, and you can always go back and see it again. All right, so we know that selective coordination is about isolating the fault or the overload condition isolating the overcurrent condition as close to the problem as possible. You want the first overcurrent device to open and nothing else in the system. That makes sure that it does a few things. And I had a really good discussion with my IBEW brethren. They said that, look, Tom, we need that isolation of the problem, because when they go into a facility, OSHA requires you just don't start turning stuff on. And because you can't just turn things on to figure out where the problem is, you need to be sure, and it's really nice to be sure, that when a device opens, you know this was the closest device to the failure, whether it be a short circuit, overload, or whatever it is. So that way, they don't have to walk into a facility with a feeder or a main, worst case, the main out, and they know that somewhere in this facility there's a problem. So it helps the electrical worker from a safety perspective identify and isolate the problem. So now, let's talk about, I'm going to hit this coordination versus selective because we're there. We're talking about it right now. So let me do this. I'm going to create a document. And what I'm going to do is I'm going to do my template. I'm going to change it to the dark. Yeah, and apply. And I'll use a white pencil. All right, now here's the trick, is if I can get this to work. Oh, it's working. All right, so I'm going to draw the time current characteristic curve. I have to draw a TCC curve. Remember, we've got current across the bottom. We have time up the side. If you don't know how to read a time current characteristic curve, it's critical that you do. You need to understand it. Download a few from the manufacturer's websites. I don't care which manufacturer you go for. Download it. If you have questions about it, shoot me an email. We'll try to help you out. So let's say, for example, since this is current, let's say that this is I don't know. Let's say this is 0 amps, and let's say this is 10,000 amps, and we'll say this is 5,000 amps. All right. Now keep in mind it's a log-to-log paper, so the increments, the distances are off in a log-to-log type of paper. So just be mindful, you might see that. In time, typically we start at 0.01 seconds. And then you'd see a 0.1 seconds. Then you'd see a 0.2 seconds, 0.3, etc., etc. Well, they're much closer together. I got a little aggressive there with my, hold on. Let me delete that. Say 0.1, say that's 0.2, say this is 1 second, etc. So it's, again, log to log. And the reason they do log to log, logarithmic in the vertical axis, logarithmic in the horizontal axis, is because if I did equidistance for every segment, let's say I go up in increments of 1 second, of 1 amp, that paper would be about a mile long that way. So to shrink it up, they go logarithmic, so that I'm basically taking this line that would be huge, and I'm shrinking it down to get the same number in. Now, I lose granularity. You lose when you're looking at the paper. You're going to lose accuracy. But in power systems engineering, you're not worried about decimals. You're not even worried about an amp. You're worried about much bigger chunks of amps, okay? Whether I'm pulling 1 amp or 2 amps, whether I'm pulling 9,001 amps versus 9,002 amps, it doesn't make a hill of difference. I'm not going to tell the difference on the curve. I might see it on my software, but in practical applications, it really doesn't matter. All right, so when we draw a diagram. So let's say I drew a diagram. I have a breaker and a breaker and a breaker. All right. And now here's the other problem. I'm showing you 3 breakers in series. Technically, at each of these panels, there's probably this going on. So don't let my drawing deceive you in thinking I've only got 3 breakers. You typically will pick the largest breaker at each panel, because if the largest breaker downstream selectively coordinates upstream, all of the smaller breakers downstream are likely to selectively coordinate as well. Because the hardest thing to do is to selectively coordinate the downstream largest breaker. If I pick the smallest, my downstream device, the trip curve. So for example, I'll just draw, say this is, I don't know, forget about the currents at the bottom. Let's say this is a 400 amp. And let's say this is, a 50 amp breaker. Because it's further to the left, my upstream device is going to be up here. This is why I say you pick the largest device, because it's the one that's going to be further, I say further to the right. And it is on the curve, further to the right. It's going to have the higher pickup amps, the higher instantaneous. The upstream device, I have to think about the instantaneous pickup to make sure that it doesn't encroach on the downstream device. So if I pick the largest device, this 400 amp, and it selectively coordinates, or even coordinates with the upstream device, I'm sure that this device that's down here is going to be perfectly fine. Hopefully that makes sense. And in reality, the faster the downstream device can go, the better off you are. You want very fast operations close to the load. That's why we put current limiting devices inside of electronics and other equipment. They'll use fuses. They'll use electronic fuses. They'll use fuses that mount to the circuit boards. You want a very fast response time. And what that does is, if your fuse is operating way over here, that gives you all of this no man's land, all of that space to be very flexible on that very first overcurrent protective device upstream. And if I can move that very first device as far to the left as I can get it, gives me breathing room for the next one up. All right, makes sense? All right, so let's go back to this. Now, I use this, and if anybody has ever watched my programs in the past, you all know I use a quiz. And I do this when I go to see consultants. I went into a consultant one time, and he says, listen, we do selective coordination for a living. Well, that's all we do. He goes, I just need you to tell me how you can save me money. I said, all right. I said, I'll do that on one condition. He goes, what's the condition? I says, that you pass a quiz, that your team passes a quiz. I said, if you pass this quiz, I will can my entire presentation, and we're going to talk solutions, products that Eaton offers for you, and how we can save you and help you with this thing we call selectivity. He says, deal. So I draw this on the screen. I draw our BAB20 downstream of an F-150, the breaker, not the truck. All right? So I'm at 0.01 seconds, and we're going to get to below 0.01 seconds in a second, Robert. And I asked the fundamental question, do these circuit breakers selectively coordinate? Does that BAB20 selectively coordinate with the F-150? And this actually happened. I'm in this meeting, And I make this agreement, and I draw that on the screen, on the whiteboard. I didn't even open my computer yet. I just got in the room. And when he walks in, he's like, throws his stuff down. He goes, look, I don't need a presentation on selective coordination. We know everything there is to know about selective coordination. I need you to tell me how you can save me money and time. So I draw these on the screen. The youngest person at the table, there was a small group, maybe 10 people in the room, in the conference room. The youngest person in that room raised her hand, and I said, do you have an answer? She says, well, not really. She goes, you didn't give us enough information. And I looked at her and I was like, what information are you needing? And she says, I need to know what the fault current is. And I'll tell you what, that was like a breath of fresh air. They did know selective coordination, because you can't answer the question if these selectively coordinate without knowing what the available fault current. So if this, I'm going to do something. I'm going to erase this guy right there. If this is the F-150 and this is the BAB 20, I need to know how much fault current is going to pass through both of those breakers. And I need to plot it on this TCC curve. So, so the reason I say that is because I can't tell you how both of these are going to operate based on current if I don't tell you how much current I expect to flow through there. So now comes the second debate. The second debate is, what current do we use? If I go back to the definition, it says for all currents from overload to the available fault current. And we know the available fault current is the three-phase bolted fault current value. Now, I have always selectively coordinated, or I even called it coordinated, to the three-phase bolted fault current value. Whenever I could not, say the three-phase bolted fault current value is, I don't know, 15,000 amps. If I put 15,000 amps through both of those breakers, I know without a shadow of a doubt they will open. How do I know that? Well, I'm glad you asked, Robert. So I know that because if I go to Eaton Selective Coordination, and you can go to any manufacturer that you feel comfortable with, Eaton, Schneider, Siemens, ABB, we all publish data, product and brochures, electrical safety reliability brochure, training tools. I want tables. That's the fuse to fuse, breaker to breaker. That's the quick spec. Let's try this one. That's not it. Hold on. Products, molded case circuit breakers. Oh, man, where is our tables at? We used to have a really nice. Where's it at? Selective coordination. I don't want SCD. I want the curves. There it is. This is fuse to fuse. Okay, here we go. Breaker to breaker. All right, so the way you read these tables, and I'm going to couch this that everybody does it a little bit different. Yes, future of AI, Omar. Oh my goodness. You hit the nail on the head, buddy. I agree with you 129.7%. I agree. So look at what this says. This says upstream breaker is on the top. I love this. Other people put the upstream breaker on the left-hand side. I have the upstream breaker on the top and the downstream fuse or breaker on the left. Okay? All of these are fuses. All of those are freaking fuses. I want a breaker downstream. Oh, man. Let me do this. Hold on. Eaton Selective Coordination. There it is. All right, I had the wrong table, but it's going to be positioned exactly the same. So I have the upstream breakers on the top, and the line side up top, and the load side down the bottom. So we said that we had an FD 150, which is there's my F frame, but it's now a PDG2. So they changed the information. I had 150, so there's my 150. There is my BAB. All right. I'm gonna zoom in. I'm gonna zoom in. So there's my 150, and there's my 20 and my 30. And when I come down from the 150 to the 30, I got 1.5. That tells me that any current over 1,500 amps is going to open both circuit breakers. We've tested these in the lab. And in fact, it tells me that 150 amp breaker, I have up to 1,500 amps for everything from a BAB 15 to a 70. So now you know, without a shadow of a doubt, that an F-150 and a BAB, the cutoff is somewhere around 1,500 amps. It's somewhere in here. Okay, 1,500 amps. Any current greater than that, I'm going to trip them both. All right, so, and that, Robert, tells you what's going on down below, because if you looked at a BAB curve, if I went like this and I drew this curve, and I know it cuts off right there, but if I drew it further down below, you would see something like this. That curve goes off to the right. And then if I did the F-150, which has the upper clearing time above 0.1 seconds, this bottom does something like that. And right where these cross, you're in the 1,500 amp range. You see what I'm saying? So below that 0.1 seconds, manufacturers probably have that data, but we just cut it off because it gets pointless at that point. So, but it's important for selectivity. But to get you to that lower number, we shot these in a lab, and we used the series ratings configuration in UL49, and we know where that crossing point is, and we plotted in that table. So manufacturers are telling you at what current value beyond which they will both open. And if you had any manufacturer who has a table like this that says breakers like this, standard thermomagnetic breakers, like say a BAB20 equivalent from another manufacturer, an F-150 equivalent from another manufacturer, if they say that they are up to 10,000 amps or the interrupting rating of the overcurrent devices, they're wrong. Period. Okay, I'm just telling you, they're wrong. All right, question it. I would say question it and ask for the test data. And you can stick it in a lab and watch it not work as well as I could. All right, so now we know current. We know that the fault current. Now, if you and I were going to argue about, you may say, Tom, you're never going to see 15,000 amps of voltage fault current value. And I will say, well, I'll never say never, but the chances are pretty low. How might I see it? I would have to bond the bus. I would have to intentionally ground something, because there would have to be zero impedance for you to get that value. So I can understand someone who says that value never occurs. So then I'll argue it, or I won't argue. I'll say, well, what about another current value? What current value would you want to coordinate to? And I was with the chair of a committee at one point. I won't say his name. We had breakfast. And I said, all right, because this is what we're arguing about, is that pickup point, or that whether you coordinate to the three-phase bolted fault current value or not. So then my question was, what's the most common fault in any power distribution system? And his answer was the ground fault. The ground fault is the most common fault in any power distribution system, hands down. So I said, all right, what percentage of the three-phase bolted fault is a typical ground fault? And he was like, well, 70, 60 some percent. I said, let's make it easy. Instead of 15,000 amps, which he had said that's the most common fault current that you would see on these types of panels in a commercial healthcare world, his argument was that the ground fault current's around 60 some percent. I said, let's make it easy. Let's make it 50%. That would be this 7,500 is your most common fault in a power distribution system. And if I put 7,500 amps through a BAB20 and an F150, I know they will both open. They will not even coordinate. Okay? So I need to understand how the overcurrent devices will respond to currents passing through them. That's a critical piece of the puzzle. And that is a fact. That is per the code, and that is per the language of the code. And NEMA has a document that tells you how to do these selective coordinations. So always reach out and verify with the manufacturer the data that you're getting, especially in these tables. Okay, so queso, it's like cheese. All right, so now I know that current makes a difference, and we can argue and debate. Do you selectively coordinate to the 15,000 amps? Do you selectively coordinate to the 7,500 amps? Which one is more common? You might say, well, the arcing current is even more common than that, so you could calculate your arcing currents and coordinate to make sure that the downstream device clears before the upstream device. It is documented in IEEE Buff Book. This process that I'm telling you, this is magic by Tom. This is not Tom's interpretation of what selective coordination is or how to do this. This is how it's done. So you do the comparison of the trip curves. When you get a current that's above the instantaneous of both, in the past, how did we fix it? We either lowered the fault current or we moved the upstream breaker to a larger breaker. The resource that you have today are the manufacturer's tables. So if I go to that, that's the Eaton. If I do Siemens, selective coordination, I'm sure tools and resources for the electrical engineering consultant, products and services. So let's scroll down, how to create a spec, write a spec. There's got to be something in here for selective coordination resources. Oh, wait, here, look. Selective coordination tables. I told you, every manufacturer will have selective coordination tables. They have the main, and then they have the branch breakers. So they do the exact same thing, and they'll tell you how to do that. So that's the Siemens references. Let's try Schneider selective coordination. They'll have tables as well. They in some, like I know Eaton, and I think Schneider has a what do you call it, software application. There's analysis tools, white papers, feature product, where to buy, where to help. Let's look at white papers. What level? Oh, there it is. See, it's a debated topic. Selective coordination to what level? Let's look at Guide to Power System Selective Coordination. There's no tables in here. I'm just looking for tables. Yep, here's their tables. So this is 240 volts, and they'll do it by voltage. You have your frame, your interrupting, your circuit breaker type. Well, that's not a table. Sorry, wrong one. Let's look at this one for panel boards. All right, here you go. There's your maximum available fault current upstream, and there's your downstream, and there's your feeder. So each manufacturer will have tables just like I showed you. The difference is going to be what's across the top and what's down the side. So each manufacturer will provide that information. But again, your big guys are pretty legit. If you come across somebody who says, "Hey, I can do the same thing, but I can coordinate all the ways up to the interrupting ratings, selectively coordinate to the interrupting ratings," be careful. Could be a marketing thing. All right, so we know that now. 0.1 seconds. All of this to help you understand that two circuit breakers in series are going to respond to a current. And depending upon the magnitude of that current will determine which one opens first or if they both open, period. Okay, the response time. If I take the BAB20 and an F150 and I throw 10,000 amps through both of those, I can guarantee they are both going to open. If I did the same thing to Square D's similar products, Siemens and ABB, you put enough current through those devices, especially up to their interrupting rating, you're going to open them both. Okay, guaranteed. Now, molded case circuit breakers. Once you get into power breakers, and you can buy a power breaker without an instantaneous. I can go up to the interrupting rating if I have a double wide, and I'll open the downstream, and the upstream is going to hold it together for up to 30 cycles. So it's all about the trip curves. Don't forget it. Now, 0.1 seconds. Let's take this same set of curves. I'm going to just redraw my thingy-me-bob, and I'm going to draw this. And there's my BAB, and there's the F150. And here is my 15,000 amps. Okay, so, and I have basically this going on. Draw a line down through it. I've got 15K passing through both of those breakers. You and I both know, based upon what we've learned, they will both open. When I do a 0.1 second, remember this is 0.01. If I'm doing a 0.1 second review, this is what I do. I take my 0.1 seconds, draw it all the way around over, and I ignore everything below that 0.1 seconds. I do this. I completely forget about the portion of the curve. Now, it could be that I have a foot coming over or whatnot. And then what I do, because this is a problem, because I know those two breakers with 15,000 amps going through both of them, I have to do something with the 15,000 amps. We ignore that. And all 0.1 seconds is doing is looking for separation of these curves in the overload region. So what that is going to guarantee for me is that if I have an overload, or if I have a very low ground fault current, because these devices will respond to a ground fault current, which we're going to get to next. It's 239. It's 1239. They will respond to a ground fault current. So, but any current less than where that pickup value is for that upstream device, I will have coordination. Any currents above that, we're not taking that into consideration because we're not evaluating we're not doing an evaluation of the response of these circuit breakers to overcurrents that include any current. And I'm not going to say just short circuit currents, because I could have a ground fault current. I could have an overload. I don't know how big the overloads could be. If it's locked rotor amps on a motor, my locked rotor amps, you add them up, they can be kind of high. So I'm just going to say generically, currents greater than the leading edge of that instantaneous pickup. If my current goes in that direction between those two devices, if I do a 0.1 second coordination, I can't tell you what will happen because that evaluation did not occur. All the qualified person did was select two breakers, hide everything below 0.1 seconds, Do not calculate the fault current. Do not do a fault current evaluation against the time current characteristic curves, and look for separation between the curves. That's all that's done. All right. That's all I'll say about that. All right. So let's go back to some questions. I know that was a long one. All right. Create notebook LM and create an agent. What do we got? Only open if they are properly maintained. Yes. all of this assumes that these products are maintained. That is a fact. Sergio Panetta, Igard in the house. I'm going to respond. We had our meeting today on direct current arc flash, and I want to give you an update on what's going on there. I'll send you a note later on. Create notebook LM and create an agent. Notebook LM. I'm not sure what that is. What about coordination for hospitals below 0.1 seconds? Okay, here's my issue, Robert. In my opinion, don't ever mention time. I know, so when you say below 0.1 seconds, it's not about, the discussion for healthcare is not about, do I go below 0.1 seconds or do I go to time zero? Means nothing. Time zero means nothing. Because even in a time zero, if I drew these two curves, okay, let's delete everything below there. This is 0.01 seconds. If you say time zero, I don't have curves that go down to 0 seconds. If you would do that, you may, if you could find curves that do that. I have coordination. I don't know. I stay away from saying time zero or to 0.01 seconds. I've heard that before. You can't do that because you need to consider current. If I looked at these two curves, I have complete separation all the ways down to 0.01 seconds. And I've heard people say, oh, forget about 0.1 seconds. We want to coordinate to 0.01 seconds. Well, these coordinate to 0.01 seconds. I got complete separation. But yet, if I've got 10,000 amps flowing through them, if I've got 5,000 amps flowing through them, if I've got 2,000 amps flowing through them, they're both going to open. So I can't just say time. I have to include current. What value of current do you want to coordinate to? If it's not the three-phase bolted fault, do you pick the most common fault in a power system, which is the ground fault? I'm good with that. If you're good with that, I'm good with that. I could stand on the witness stand and defend that action, I think. Anyway, lots of commercial interpretations. I don't know. I'd love to know which one's a commercial interpretation, because everything I've said so far is all factual. The only thing that's different is whether or not a manufacturer publishes the right data. So I do question some manufacturers' data, because I don't know if it was written by a commercial person or an engineering person. I've seen things where the ratio tables will say, oh, these two breakers will selectively coordinate up to 10,000 amps, and it ain't going to happen. They mean coordinate at 0.1 seconds, and you can't throw amps in there, because the moment you throw amps in, now you're into the selective coordination discussion or a coordination discussion that's not a 0.1 seconds thing. So that's my only thing there. What is the NEMA document? Oh, that's a good question. So we're going to do this together. Put my coffee cup over, and we're going to say NEMA selective coordination. I believe it is free. There it is. I will put it in the chat. Control C, Control V. It's a free download, or you can buy a hard copy for apparently 146 smackaroos. And let's do this. How do I get out of there? Boom. There's your selective coordination, low voltage circuit breakers. We describe selectivity. Am I showing anything? And the stuff that I just talked about, and why I think if you're not a NEMA, here's what I think. I've come across some marketing literature that is just bogus. You got to be careful what you read, and always ask questions if it doesn't smell right. There's the selective coordination requirements, fire pumps, and this puts all the different sections, but more, and you even talk about the code interpretation examples, all that good stuff. So this is a great reference for you. A lot of what I just talked about is in this document. I helped put it together. The fact that you can have the instantaneouses move. You could have trip units that can get kind of fancy schmancy. Here's the discussion that I just had with this. So what I'm sharing with you is an industry thing. I'm not sharing. I didn't even tell you what my opinion was. I didn't tell you whether or not I liked coordination or selective coordination. I didn't tell you anything, right? All I told you was what the code says and how breakers respond to current. If you understand that fundamental, that breakers and fuses are going to respond to current passing through them. The moment you see something like it's in Article 517 where it says you only are looking for the separation of trip curves. There's no consideration of fault current. And when you have an overlap, you ignore the overlap below 0.1 seconds. You're not doing something. So at least you understand that when you coordinate to 0.1 seconds, you know what is not getting done, and you know what happens if the currents are higher than you expect. That's all. That's all I'm saying. So Felix, thanks for asking that question. I just shared that with you. Boy, where was I? What is the NEMA document? Oh, there we go. Wrong link. Dan, Tom mentioned there was a NEMA document. Sorry about it, guys. I got it to you. On tested combinations on the fuse side, is there ever a set of circumstances where a 2-to-1 ratio is not effective? Yes. So, in fact, good question. Good question, Steve. So, on the fuse side, here's the thing. A lot of people will say, selective, I'm just going to go Eaton, selective coordination, because we have Bussmann, and we have tables. So a lot of people automatically think that if I have fuses, it's 2-to-1. Not true. Because, and this table will tell you the story. So again, now I love the Bussmann guys did it backwards. They put the downstream up top, and they put the upstream down the bottom on the left. So, and I tried to get them to change that, and it was not going to happen. So anyway, we have the upstream device. Say it is a KRP, whatever. Here's a 2-to-1, and then there's a 2.5-to-1. There's a 2-to-1. So there's a 2.5. So I have to do 2.5-to-1, which means I'll put a little bit larger. Here's what a 2-to-1 ratio means. If I have a 100 amp breaker downstream or a 100 amp fuse downstream, I need a 200 amp or larger upstream. So if I had a 100 amp downstream and it was a 2.5, I'd need a 250 amp or larger fuse upstream. to get selective coordination all the way up to 200,000 amps. So it doesn't matter how much current you pump through these fuses, as long as you maintain, in this case, 2 to 1, but also 2.5 to 1. Now, if you look at the limitrons, and you have an upstream or a downstream of an FRN, I need a 4 to 1 ratio. If I have the FRN downstream of a LPNRK, I have an 8 to 1. So if I have a 100 amp fuse downstream, that means I need 800 amps of fuse upstream. So you go to the tables, and it's not a true statement to say all fuses are 2 to 1. Okay? The fast-acting fuses are that way. You'll see a lot of 2 to 1s. If I've got an LPJ downstream, I can put an LPJ at 2 to 1, 2 to 1 in here. It even gets better at 1.5 to 1. Now here's a 3 to 1 if I have the KTUs or a KTN, a JJN, JKS. So you've got to always go back to the manufacturer's tables to understand, when I have two devices in series with each other, how much current can I pass through there? If I maintain the ratios, that's telling me I can put up to 200,000 amps through both fuses. The downstream will open and the upstream will not, right? So if I had an LPJ, if I had an LPJ 30 downstream of a KLU 60, and I put 200,000 amps through both of those fuses, that LPJ downstream fuse, 30 amp fuse, is going to trip first before that 60 amp fuse upstream. All right, so hopefully that answers that one. Untested combinations with fuse slides. Hey, Thomas Yingling, have fun in your meeting, buddy. But don't NFPA codes and standards require that coordination? No. Okay, so there are some places in Article 700 where there's a requirement for selective coordination. But here's what it says. In fact, let me go back to 517 on coordination. If you go to 517, what it says for healthcare, Control F, coordination. Here we go. It says overcurrent devices serving the essential electrical system shall be coordinated for the period of time that a fault's duration extends beyond 0.1 seconds. So I would look at that 0.1 second line and say, I only have to worry about any current that would go beyond 0.1 seconds. So that is, if I draw my 0.1 second line, that is everything over here and down, right? So it's only looking at those overloads. And if I selectively coordinate, I'm going to meet the coordination rules. Okay, so the code is not mandating that you do coordination and you never do selective. I can do a selective coordination in a healthcare. A lot of healthcare engineers do that. But it doesn't mandate selectivity. It just says it has to be coordinated. Lots of commercial interruptions. Oh, okay. I'm like, okay, I thought, because thanks. I love you, brother. I love you, brother. All right, there's my NEMA. There's Felix. Thanks, Felix. It's 12:55. Your answer means they always have to go to the tables, and labeling is just critical. Only if the fault currents are high enough. Okay, and Steve, I would argue, I agree with you. The fault currents are typically high enough; they're in the instantaneous region of most of these breakers. So you're gonna be using those tables a lot. All right, ground fault currents. Here's what I'll say on ground fault currents. These curves, these curves, these curves are crying. These curves basically will respond to a ground fault current because remember, if I think about a breaker, if I have a circuit breaker, in that circuit breaker, I've got 3 switches. If I have a ground fault current that's flowing through this, if I go upstream and I have a zero sequence CT, it's going to see it, but so will that pole. And that pole, if I have 3 poles and I have a ground fault current flowing through one of those poles, that one pole is going to respond to that current. It's going to be a lower magnitude, but it will be seen in one pole. That one pole will have to respond. All right? So that's an important piece of this puzzle. Okay? So these devices will respond, but you're not going to see the 15,000 amps. Let's say that the ground fault currents are really low and it's going to be somewhere in this range. That F150 is, if it's greater than 150 amps, it's going to respond somewhere up in that time period. It's going to give that downstream breaker enough time to react because that single pole, you're already in the instantaneous region for a single pole device. And I'll tell you, some manufacturers will plot trip curves, and they'll tell you if for a single full pole or a 2-pole fault, the curve is different. And the reason that is because in some of these circuit breakers, and I'm going to do this and I have to run. In some of these circuit breakers, when you have a mechanism, you have this like this going on, right? The way some of these, and you have I don't know, say an arm here that controls the contacts, right? In some cases, it's one mechanism that operates off of the fault current. And that one mechanism, if I only have one pole that is pulling and seeing the current, then the force on that mechanism is going to be lighter, which may mean it takes longer to open, okay? Or I might need a little bit more current if it's one pole trying to open all 3 poles. In many cases, there's a mechanism for each pole so that I don't see a response in the time current characteristic curve. And the TCC curve that you see plotted is the same whether it's a single phase, 2 phases, or 3 phases. So be careful, take a look at the time current characteristic curves for any differences there. All right. So it is 12:59. I'm chairing a 1:00 meeting. So I hope you guys and gals got something out of this. We'll go live again. Maybe next Friday. I'm going to try. I'm going to be in Lisbon, Portugal, but I might be able to go live. Anyway, take care, stay safe, and please stay happy.